Well, hello again. These are the problems for chapter 1 in the section 2, and we were up to, I think, question 11, and we're going to do 11 through to 16 to the bottom. So here we have, again, you might like to try these problems yourself and then before having a look at the solutions. So suppose P is a prime and P is 1 mod 4. We want to prove the product of the quadratic residues mod P is minus 1. And then we ask the question, well, what happens if P is 3 mod 4? And here is the solution to this. Now we want the product of the squares. So we're starting off with a prime P, which is 1 mod 4, and we're going to use Wilson's theorem, which we proved several times. We proved it in the earlier problems as well. So I'm going to start off by looking at the product of the numbers 1 up to P minus 1 is congruent to minus 1 mod P. And we do a standard trick here. We look at this product and we stop halfway, and then we can write from this end we can write we can write the next term as P plus 1 over 2 up to P minus 1, and then we can read all of these numbers here modulo P. So copy those down, and probably easiest to read it from this end backwards. So P minus 1 is minus 1 mod P, P minus 2 is minus 2 mod P, and P plus 1 on 2, which is P minus this, is minus this modulo P. Now, of course, these numbers here are exactly the same as these ones, except we've got lots of minuses, and in fact we have P minus 1 over 2 negative signs, and we get each one of these repeated, so there's our squares. We wanted the product of the residue of the quadratic residues, and well, these are all the quadratic residues, and so their product times this is minus 1 mod P. Now P is a 1 mod 4 prime, so P minus 1 I should say over 2 is even. P minus 1 over 2 is even, so that's 1, and that means this is then just congruent to minus 1 mod P. In the case of a 3 mod 4 prime, well, exactly the same computations, except this one is going to be odd, so in this case the product will be 1. So once again we see this really interesting divergence, this dichotomy between the 1 mod 4 primes and the 3 mod 4 primes. They really do behave quite differently, and it's just yet another example of how of this in action. Okay, question 12. It says if for P prime we want the set of quadratic residues mod P forms a subgroup of UP. And here is the solution of that. So let's give it a name, call it Q to be the set of all quadratic residues in UP. Well, 1 is there because 1 is a quadratic residue. And if I take two objects A and B in this set Q of quadratic residues, then they got there because their Legendre symbol, A over P and B over P, were equal to 1. And that's true if and only if the product of these is equal to 1, and that means that AB is a quadratic residue. Finally, we need to, associativity is obvious, we just need to check the inverses. So if A over P is 1, that means A is a square modulo P, so that means A is the square of something for some x in UP. So the inverse of A then is x inverse squared mod P, and that means A inverse is a square, so A inverse is in the set of quadratic residues, and therefore it forms a subgroup. So I should finish there with therefore Q is a subgroup of UP, under multiplication, of course. Now question 13 is a nice little problem here. It says suppose Q and we take 4Q plus 1, call that P, And we're going to suppose that both of these, the q and the p, are both prime. We want to prove that 2 to the 2q is congruent to minus 1 mod p, and that's not very exciting, but this is. We can now deduce that 2 is a primitive root mod p. 2 is a primitive root mod p. And I'll give us a little hint there. If p is 5 mod 8, what does it tell us about the number 2 in ZP? Well, we'll see how that fits into the problem as we go. So here's the solution for 13. So we're given that q and 4q plus 1 are both primes. Q is not 2, because then 4 2s are 8 plus 1 is 9 is not prime. So q is not 2. So that means q is an odd number for some k. And I can plug that in, and now I get p is 8k plus 5, which is congruent to 5 mod 8. And hence, that is connected with their hint. Now we know that if p is 5 mod 8, then we saw before that 2 is we know that 2 is a quadratic non-residue. That's easy to show. So that means 2 over p is minus 1. And then using Euler's criterion, this is 2 to the p minus 1 over 2 is minus 1 mod p. And p minus 1 over 2 is 2q. So that gets the first part out. Now p minus 1 then is 2 squared times q, because p was 4q. So the only possible orders are going to be, the only possible orders for 2 are going to be this divided by q, which is 4, or this divided by 2, which is 2q. That's how we check. You take your p minus 1 and you divide it by each of its prime factors, and you only need to check those powers of the given a that you're studying. So this divided by q would give me 2, this divided by 2 gives me 2q. We've just proven that 2 to the 2q is not 1, it's minus 1 mod p, and 2 to the 4th is 16. And if that were the case, that would give you q as 1, which is impossible. And so therefore 2 must be a primitive root modulo p. Question 14, sort of similar ideas to that one. We've got p is 3 mod 4, and q is 2p plus 1, and these are both prime. And we've got 3 parts to this. We want to show that 2 over q is 1. Use Euler's criterion to deduce that 2 to the p is 1 mod q, and find a prime factor of 2 to the 251 minus 1. Which is a nice little corollary to this. So here is the worked solution. So we're given the information p is 3 mod 4, and q is 2p plus 1, which are both prime. So we're looking at 2 over q. So 2 over q, we use our special formula for 2 over q, which is minus 1 to the q squared minus 1 over 8. That's that standard formula for when you've got 2 over a prime. Now I can factorise the top as q minus 1, q plus 1, because I've got some information here about q minus 1. So I plug that in terms of p's, cancel out a little bit. I've got a 2 there and a 2 there, so I can reduce that down to minus 1 to the p plus 1 over 2. And remember that p was a 3 mod 4 prime, so p is 3 plus 4 times k, and so I can plug that in here. And so I should perhaps in brackets say we write p as 3k plus 4 for some integer k. And now once we get to here, that 2 goes into that one, and you get 2k plus 2, which is even, so minus 1 to an even power is going to give me 1. So that gets me that part. 2 over q is 1. I can now just apply Euler, and that's going to be 2 to the q minus 1 over 2, and q minus 1 over 2 of course is p, so 2 to the p is 1 mod q. For the little rider with this one, we take p now as 251, which is this is a prime number, and it happens to be 3 mod 4. So by the way, that means that 2 to the 251 minus 1 could have been a Mersenne prime, but it's not, because we're going to show it's divisible by 503, but it's of that form 2 to the p minus 1. So if nothing else, it provides another counterexample to the fact that if 2 to the p minus 1 is prime, if p is prime, then 2 to the p minus 1 is not necessarily prime. Anyway, so we do that, and then we double this and add 1, and that gives me 503. And that we've seen up here that 2 to the 251 is congruent to 1 mod 503. So 503 is a factor of, that's a factor of 2 to the 251 minus 1. Question 15, we're going to explain why every primitive root modulo a prime p must also be a quadratic non-residue. Let's sort of think about it for a minute. It makes a lot of sense. Every primitive root must be a quadratic non-residue. And then the rider is how many quadratic non-residues are there in Z47 which are not primitive roots? So how many quadratic so the converse is false, of course. Just because you're a quadratic non-residue doesn't make you a primitive root. And we want to find how many of these quadratic non-residues in Z47 are not primitive roots, and can we find them? So here's a little solution to question 15. So if G is a primitive root, then that means the Legendre symbol G over P by Euler is congruent to G to the P minus 1 over 2, that's Euler. And if G is a primitive root, then G to the P minus 1 over 2 we know is minus 1 mod P, and that tells me that G is a quadratic non-residue. Converse, of course, is false. Now in Z47, then the number of primitive roots is 546, and 546 happens to be 22. So that means there are 22 primitive roots in Z47. And of course, p minus 1, take out 0, you get 46 non-zero numbers. Half of them are quadratic, half of them are squares and half are non-squares. So there are 23 quadratic non-residues. So there's only one quadratic non-residue which is not a primitive root. Sorry, my English there. So the only quadratic non-residue which is not a primitive root is minus 1, because obviously minus 1 is not a primitive root, but it's not a quadratic non-residue here because it's it's not a square, I should say, here, because 47 is congruent to 3 mod 4, so we know minus 1 doesn't have a square root. So minus 1 is the only quadratic non-residue which is not a primitive root. And that's where we found the missing one. Last one for this section, if similar to the ideas above, if P and 2p plus 1 are both odd primes, we want to show that minus 4 is a primitive root, and 2 times minus 1 to the p minus 1 on 2 is a primitive root. And the worked solution to that is here. So again, we've got p and q is 2p plus 1 are both prime. Then that means q minus 1 is 2p. So we only need to check then the prime factor, and the p is an odd prime, so the only things we have to check are this divided by p, which is 2, and this divided by 2, which is p. So I just need to check that minus 4 to the q minus 1 over 2 is not 1. So q minus 1 over 2 is minus 4 to the p. So this is minus, this is an odd prime, so this is, we're going to take a negative out, and 4 to the p is 2 to the 2p, and we've seen before that that is minus 1 modulo q q. And similarly, minus 4 to the p minus 1 over p just gives me 16, and 16 is not 1, because then we would need this prime to be 15, and so it's not a prime. So minus 4 is a primitive root modulo q. Or for the second one, we take g to be twice minus 1 to the p minus 1 over 2. Now you've got some cases here. If p is a 1 mod 4 prime, then that means my q is 3 mod 8, because q is 2p plus 1. And we've seen there before that q is a quadratic non-residue for the 3 mod 8 primes. And by Euler, we can then write 2 to the q minus 1 over 2 is minus 1. So this is equal to minus 1. So in that case, our g is a primitive root. If p minus 1 over 2 is even, then minus 1 to the p minus 1 over 2, sorry, I'm doing each of the 2 bits of this, aren't I? So minus 1 to the p minus 1 over 2 is 1, because this is even. So this one, so g to the q minus 1 over 2 is not 1. Also, if I take g to the p minus 1 over p, we have to check the both cases, then I get g squared, and that's congruent to 4, which is 0 mod, which is not congruent to 1 mod q. So therefore g can't have order q minus 1 over 2 either, and that tells me then finally that g is a primitive root. Now that was all on the case p is a 1 mod 4 prime, and we use a similar argument to show it holds also if it's a 3 mod 4 prime. So they are the tutorial problems for that particular section.